everyone. Thank you for coming to all of our presentations tonight. We really appreciate it. My name is James Wadsworth, a member of the 2019 MSGIST cohort, and I'm also a GIS analyst for the Enterprise GIS team at the Department of Planning, Design, and Construction here at the U of A. My talk is focused on 3D GIS visualizations, particularly focused on the university scale, which is kind of similar to some really small governments. So I'm going to start by kind of introducing the study area and the rationale for examining why you would want to do 3D visualizations. Then I'll talk about some 3D GIS kind of broadly, and we'll look at some case studies that have been done at the U of A. Then after that, I'll talk about the 3D building models that I explored as a part of this project. And finally, I'll talk about how we can integrate those models into web map applications. So the study area here is the planning area boundary for the University of Arizona main campus. It extends the northern extent from Lester Street south to 8th Street, and then on the east side, on the east side, Campbell Avenue to the west side, Euclid Avenue. It's about half a square mile, and it has 300 university-owned buildings, in addition to many non-U of A-owned buildings. But for my purposes, I examined only the U of A buildings. The university presents kind of an interesting group of people in terms of who is actually looking for data and how they use it. And so they span a wide variety of roles, varying from students, staff, faculty, and then visitors who are community members that are also looking to engage with campus. And then they all have different use cases for our data. So students and faculty might be looking for classrooms. The staff actually ingest some of our data to do analysis with, and then visitors kind of do whatever they want. They can do everything. So typically that data is presented in 2 dimensions as well. Not a lot of 3D apps are out there, and that's something that we're exploring. And so my research questions were, what methods exist to leverage 3D GIS data that can be used by all of these different types of people? And then something else to think about that's important is that the University of Arizona actually has had GIS in some form or another for decades. As a part of the Enterprise GIS team, Grant McCormick has done a lot of work developing that data set, and students along the way and other staff. And not everyone has this kind of huge foundational data set to really build on and do some of the complex stuff. So my other question is, how can you employ some form of 3D GIS with varying quality of data? If you only have your building footprints, or you don't have everything that you need to really go all out here. So at this point, as I said, we've had some kind of GIS at the U of A for decades. And I want to stress that I didn't do all of this myself. Some of this was done before I got here. Some of the foundational data was created before I got here. And I'm really lucky to have had the opportunity to work with it and expand on it. So this is an example of our visitor map. It's traditional 2D GIS. It's got a bunch of labels. It has point symbols, polygons. It's got some lines on there. And it's really good for orienting people who are able to interact with those things. But if you took away all of the labels and the legend at the top, then you would start to see people having issues with actually finding where they are and how to navigate places. And that's something that 3D GIS does really well, is that it represents reality in such a way that it's easier to kind of relate to how you have interacted with it in real life. So here you can see several buildings that have kind of interesting facades going up and down that aren't clearly conveyed in a 2D format. And so a person who looks at this map kind of immediately identifies, there's a stadium, I know where that is, I need to go this way, I recognize the storm, etc. So in 2D GIS, you use points, lines, and polygons, and those typically only contain 2-dimensional data. It's possible to encode some z-value data into those features, but then to actually view that in 3D, you have to manipulate it in the scene view or by using extrusion expressions to kind of artificially create these 3D features. But what Esri's done recently is create a new kind of geometry called multipatch geometry. And that actually includes all 3 coordinates in the geometry for each point. So you can see the x, y, and z for the selected feature on the right. And what that means is that because it's encoded in the geometry, if you had a project set up with these 3D features in it, you could take that layer and put it into a brand new, fresh project, and it loads in 3D perfectly. You can set it to maintain the symbology as well, and that gets rid of the need to kind of go through the process of making sure your scene is set up properly, and each of your layers has the appropriate symbol and appearance settings. So not only does it maintain the true geometry, but it's really easy to work with as well. So these are some of the examples that I said we were going to talk about that the U of A has done before. This is an older map that was created using ArcMap and ArcScene, and it's visualizing buildings on campus, their true height, and then they're colored by the age that they were constructed. And so you can see very clearly which buildings were created when, and it's a cool visualization of how the campus has kind of grown over time. This is a different kind of visualization in 3D where the color is actually related to the value of the building and the height is related to the age. So you can see that the tall, light buildings are old and what facilities management has determined to be less valuable. And the shorter, dark buildings are kind of new buildings that have a lot of improvements and technology in them. And this map was used to kind of guide decision-making on what buildings really needed to be renovated and other decisions like that. This is more of your kind of typical 3D GIS view. It's presenting a proposed construction site, all of these new buildings in red that would potentially be impacting the streets and altering the skyline. And this was used for a presentation to people who were not super familiar with the campus from a top-down view. And it clearly displayed where the impact was going to be and what kind of structures would be changing in that area. Some analysis we've done in the past is related to the 3D that you can't really do in 2D. This is actually a proposed building near the Banner Health Center up north. On the right, you can see this is the new building, and this is one of Banner Hospital's buildings that has a helipad on top. And before we could begin construction, we had to determine if the height of the building would impact the incoming and outgoing helicopter flights. And so as a result of this analysis, they actually incorporated some of our findings into the final build design. And from there, it's a really positive example of how 3D GIS can do things that 2D can't. This is a fly-through animation that we created to highlight upcoming capital development projects, and we presented this to the Arizona Board of Regents. It was very positively received. You can see that it changes the symbology as the video progresses. We exported it from ArcGIS Pro, and it was compatible with other video editing software, so we were able to add in this 3D text. It consumed all of our base GIS layers, and it's a similar process as to how I'll explain. I did it in the future. But this was really effective for showing what buildings will change and what buildings will actually be created in space that doesn't have anything in them right now. So I'll just finish letting this play out. You can see some of the new buildings that are actually going to be developed right now and are upcoming in the few coming years. So now I'm actually going to talk about the specific 3D models for this project, the 3D models as a group of kind of ways to approach these different things depending on the levels of data you have. So here you can see what I'm calling simple buildings. These are created from a single polygon. It could be a building footprint or a building roof outline, and it's extruded to a specific height that's encoded in the attributes of that polygon. So in this example, I had a number of floors, and I made an extrusion expression that multiplied that number of floors by an average floor height, which is about 12 feet. And then from there, I could use all the other attributes in the polygon layer to do some thematic symbolization. So you can see some residence halls, academic buildings, athletic facilities, etc. What I've called intermediate buildings are, they're a little bit more advanced. They have a similar concept, but now there's a floor plate polygon for every floor in the building opposed to a single polygon representing the building. And so it requires much more data and a lot more kind of processing on the back end, but it lets you refine the exterior of the buildings in ways that you couldn't do with a single polygon. You also have to have specific floor height attribute information for each floor rather than just an arbitrary number of floors. And then it also takes into consideration the roof forms of the buildings. So the elevations of these roof forms were either taken from construction drawings or were calculated from using sources like pictometry. And encoding those actually into the vertices allows for really kind of unique roof forms to be visualized. Then the third category is advanced buildings, and there's two types of advanced buildings that I looked at. This is an example of the CATS Academic Center on campus as a photorealistic building. And what I'm really excited about photorealistic buildings is that it's kind of, it has a ton of far-reaching possibilities. So you can use this for all kinds of purposes, like integration in the web apps. It could be used in virtual reality. There's just a number of things that you can do at this point that you can do with the non-photorealistic buildings, but it really brings you into the experience and helps orient you in a way that you can't do without these textures. So this has the similar structure as the intermediate buildings, but it also has kind of an exterior feature class that then you can edit as a multi-patch feature and create things on the facades and the structure of the building that exist at a smaller scale even than the floor level. So if you look on the corner of the building here, there's actually a protrusion. There's a big sign that was put up there. By editing multi-patch features, you can create exact sizes and extrude that a specific amount, and it lets you add a lot more detail. The downside to the photorealistic buildings is that you have to have an image for each face, and it can be really tedious and difficult to kind of get those textures to line up properly. And then you also have to deal with storing all of those photos. But multi-patch features actually store the texture in their geometry as well, or in their data. So these textures will also be applied if you load them in different places. The second type of building is what I'm calling an expanded building. And this is a zoomed-in rendering of the administration building on campus. It actually has 3 floors above the top of this graphic. But here you can see that it has a detailed interior floor print that leverages our CAD data. And each of those polygons is clickable and has spatial information. It's symbolized using the department ownership. So each of those different colors represents a different department, and that'll be updated live as our space data gets updated. It's a kind of a foundational requirement for developing interior navigation to have something like this so that you can really visualize the change from a place that kind of occupies the same XY but a different Z. So finally, I'm just going to go really quickly through our web application, or through how you could create a web application. And basically all you have to do is get your 2D feature class data into multi-patch data, which is a requirement for being ingested in ArcGIS Online web scene, which you do by extruding and then running through a geoprocessing tool. And then you publish that into ArcGIS Online. So you take your locally stored data and you can export either individual layers or the entire scene layer package as an item. And then you upload that content to ArcGIS Online as you would any other layer. From there, you would create a web scene in ArcGIS Online. You can see here, I've ingested all of these layers on the left. I've tested that they're visualized properly here. I set a custom extent and zoom, and I updated the sharing properties so that it would be properly ingested by everybody else who went to the app. Then from there, I take that web scene into Web App Builder, and I can add all kinds of widgets. So I can let you toggle different layers here. You can adjust the illumination angle and the contrast. And again, you have to change the sharing settings here to make sure that nothing breaks along the way. So in conclusion, 3D GIS provides building models that can work for every level of data that you have. It gives you a unique vantage point, so you can see things that are impossible to see in real life, like this exaggerated building. And then it lets you can use web applications to really get at any specific use case you have. This is a visualization from our UA 3D map online that shows CAT-TRAN routes and then properly oriented stops and lets you get context for where those stops are actually located on a similar reference frame like I was talking about. So with that, I want to thank you for your time, and I want to thank the Department of Planning, Design, and Construction and the School of Geography and Development, and also my team at the UA Enterprise GIS. Are there any questions?